In this video, we're going to be covering sets. Hopefully you covered a little bit about sets in your discrete math class. If you need a little bit of a refresher though, stick around for this video. The most important thing to note about sets is that sets have members. So every set contains some elements. For instance, this contains 4, hello, 3.14, and the Greek symbol omega. The order that the members of a set appear don't bear any relevance. So 4 hello 3.14 omega has exactly the same members as hello 3.144 omega. The only property that a set has is its members. So it doesn't matter how you chose the members or how you wrote them down or the order you wrote it down. All that matters is what is actually in the set. So for instance, the set 0, 1, 2, 3 is the same set as the set of all digits in 3102. A set can also have no members. A set with no members we typically call the empty set. And we can say that this is the empty set because all sets with no members have the same members, and so they're all the same set. We typically denote the empty set with either empty curly braces or this null symbol. A set could also have an infinite number of members. So for instance, the set of all natural numbers, 0, 1, 2, 3, 4, etc., has an infinite number of members. In addition, if we consider the set of prime numbers, there's an infinite number of those. Or if we considered all powers of 2, for instance, 1, 1/2, 1/4, 1/8, and so forth, there's an infinite number of those as well. A set could also contain other sets as its members. So for instance, this set has 4 different members. The first member is 1, the second is the set containing 1, the third is the set containing 2, 3, 4, and then the fourth is a set containing 6 and a set containing 7, 8, and 9. Each set has a size, which we typically call the cardinality, that refers to the number of members that belong to the set. The notation for the set's cardinality are these 2 bars on either side of the set. So if we look at some of our examples, the set hello 3.144 omega has 4 elements in it, so we say it has cardinality 4. The empty set has 0 elements in it, so we say it has cardinality 0. This weird set from the last slide that contains other sets as members, well, that only has 4 things in it, where some of those things have their own cardinalities. And the set of all natural numbers has an infinite cardinality. We're going to be talking more about that one later. These are a few common sets that we're going to be using a lot throughout this semester. So the first one is the natural numbers, which are all of the whole numbers starting with 0 and going through infinity. And yes, 0 is a natural number for this course. The integers are all of the positive and negative whole numbers, including 0. The rationals are all of the positive and negative numbers that can be represented as fractions. So for instance, 0 or -1/2 or 1/2 or 5/17 or 17/5. The real numbers are all of the numbers that can be represented with a potentially infinite decimal representation. So for instance, pi is a real number, 0 is a real number, -pi is a real number, so is the square root of 2. The binary set contains just 0 and 1, and the decimal set contains all of the digits in our decimal representation of numbers, so 0 through 9. There are certain things we'd like to assert about sets. Those are propositions we can make about sets, so true-false statements. One example of a proposition is this membership proposition. So if we say X is a member of S, that's going to be true whenever X is among S's members. And we typically read that as either X is a member of S, X is in S, or S contains X. So for example, 2 is a member of 3102, but 4 is not. We could also say the opposite, which is that X is not a member of S. These propositions regard the relationships between 2 sets. So this first one on the left says that S is a subset of T, which is going to be true if all of the members of S are also members of T. So for example, 203 is a subset of 3102 because all of the elements on the left appear in the right. 243, however, is not a subset of 3102 since 3102 does not have 4, and 3102 is a subset of 0, 1, 2, 3 because everything on the left appears on the right. In the right-hand column, we have that S is a superset of T, which is saying that everything that is in T appears in S. So it's just the same as saying T is a subset of S. Similar to subset and superset, here we have proper subset and proper superset. So if you think of subset as a less than or equal to relationship, proper subset is more of a less than relationship. So S is a proper subset of T if everything that belongs to S also belongs to T, but there is at least one thing from T that does not belong to S. 203 was a subset of 3102, and it is also a proper subset of 3102, since 1 appears on the right, but it does not appear on the left. 243 was not a subset of 3102, so it is also not a proper subset, and 3102 is not a proper subset of 0123, since both sets have the same elements. There's nothing on the right that did not appear on the left. Here we have operations that we perform on sets. Each of these operations is going to start with sets as input and then produce different sets as output. The first operation is the union operation. That symbol in the middle is meant to look sort of like an OR because it's kind of an OR relationship between those two sets. The union of S and T is the set of all elements that are in S or T. The intersection of S with T is S intersect T. That symbol looks kind of like an AND symbol because it contains all of the elements that are in both S and T. The complement of S means all of the elements that are not in S. Now you have to be very careful when you're looking at the complement because when you say the things that are not in S, you need to consider, well, what is the universe of things that we're talking about here? So for instance, if I had S was all of the even natural numbers, and I took the complement of that, you might ask this question, is -1 in the complement of that? Or how about -2? Or how about my left shoe? Or something like that. So typically, you're going to need to identify some sort of universe for your set. So if we said the universe for the set was all of the natural numbers, then the complement of 0, 2, 4, 6, 8, etc. are all of the odd natural numbers, so 1, 3, 5, 7, 9, etc. If we picked a different universe, that complement would have been different as well. In most circumstances, the universe is going to be sort of implicit based on the context of that set, but if you're confused, then it's best to try to ask or identify what the universe should be. The difference between set S and T are all of the elements that belong to set S but do not belong to the set T. You can also think about this as S intersected with the complement of T. And then we're going to get to the power set and the Cartesian or cross product in the next slide. The power set of a set S, which is going to be denoted as either pow of S or sometimes P of S or 2 to the power of the set S, is going to take a set as input and produce a set of sets as output. That output set will contain all of the subsets of the original set S. So for instance, we have all of the sets of size 0, which is just going to be the empty set, all of the sets of size 1, so that's, in this example, the set containing 0, the set containing 1, the set containing 2, and the set containing 3. And then we have all subsets of S that have size 2, and then all subsets that have size 3, etc. And then also the set S itself is a member of the power set of S, since it is a subset of itself. The Cartesian or cross product of a set takes two sets as input and then produces a set of ordered pairs as output. So the Cartesian product of S and T are all of the pairs where the first thing in the pair came from S and the second thing came from T. So for example, if we looked at 0, 1, 2, cross product 0, 2, 4, we end up with 9 elements in the resulting set where we have 0 paired with all of the things from the second set, 1 paired with all of the things from the second set, and 2 paired with all of the things from the second set in that order. The final thing we're going to be talking about with regards to sets is something called set builder notation. So set builder notation gives us a way of describing the elements in sets without using intersections or unions or trying to list all of the elements. So some sets, it's going to be best for us to describe properties of elements that are going to be in those sets, rather than try to build them from other sets. The idea for set builder notation is that you're going to be filtering elements out of some other set by using a predicate. So here on the slide, you see an example of set builder notation, where we say the set T is all of the elements where you took some element X from the set S and then chose to include it in T, provided that the predicate, when applied to X, was true. So you can think of this predicate as filtering out elements from S, where only the true ones end up in T. The way that we would read this set builder notation is the set T is equal to all of the elements X from S, such that P of X. We would read this example on the bottom of the slide as all of the natural numbers X, such that the square root of X belongs to the natural numbers. In other words, that example refers to the set of all perfect squares.